All right, so we're going to go ahead and move on to lesson 3. So we've done wave characteristics. We've done just waves, what they are, wave characteristics, and just we've done waves. Okay, so we're getting into wave interactions. So the 3 real wave interactions that we're going to look at are reflection, diffraction, and refraction. I'll move my guy up here. So all of these, we think of them reflection usually as in light. We think of you probably don't ever think of diffraction, and refraction you've probably seen when you're in a swimming pool or something. Okay, so we're going to kind of take a look at what all of those are. So reflection is simply the bouncing back of waves on surfaces that they can't pass through. Okay, and this can happen on all different types of waves, right? Light reflection, you guys have seen. You've seen mirrors. You've probably seen, reflecting off of water. But think of sound wave reflections, like echoes, and even water reflections. If you jump into a pool and those waves travel outward, what happens when it hits the edge of the pool? Well, they bounce back and they actually start interfering with the waves coming this way, but they're bouncing back and they're reflecting off the side of that pool. Okay, so that's what reflection is. So you can see here, this is a laser pointer that I have in a beaker full of water. The light comes through this way and actually can't pass through that glass and bounces this way. And if you can see it, you can barely see it this way, but it would keep going around and around if the energy didn't disperse. Okay, same here. It comes up for whatever reason. It can't pass through that water barrier. There's not enough energy, and so it bounces back. So that's reflection of light in maybe a way that you haven't seen it. Now, diffraction is the bending of waves around an edge. So it's a little bit different than reflection. So this is the reason why we can hear sounds that aren't in the same room as us. So if you were in my classroom, okay, the door is over here. There's a big long hallway with other classrooms. Sometimes we can hear what other classrooms are doing. Well, why can we do that? Because we're not sitting in that same classroom. Well, a little bit of it might be coming through the walls, but most of it is the sound waves exiting their room, bending around, and then bending into our room, bending around the edge of their door, and then bending into our door. So the waves travel out a door with one room, bend around the door, so the next room is able to hear it. This is why, let me go back. This is why, if I had a box of, basically just a box and a dark room and a flashlight, and I turn that flashlight on, why could you see if you were on the other side, or let's say a wall or whatever? Why can you see that light? Well, it's because light can actually bend around at pretty heavy degree angles, and you can see that light. Okay, so diffraction's happening all the time. You probably just don't really think about it, especially with light and sound. Now, refraction is a wave that can bend, but this is they're bending because they're passing through different mediums, not because they're coming to an edge. Okay, so this is refraction. The light waves reach your eyes at different angles because they travel in different speeds in different mediums. So remember that. We learned that in lesson 1 or 2. But the waves reach your eyes at different angles because they're in different objects. So the objects appear to be broken. So you can see the light coming through here. It refracts and then comes out the other way. So here in this picture, I have the laser pointer pointed basically down like this. And you can see that some of that light reflects here. So you can kind of see at the angle I have it, but some of it refracts and bends through this water. So you can see this little beam of light. If you think about that, it kind of doesn't make sense because I have the light pointed straight down. Well, it's going through that glass and then through that water, and now it's bending. Okay, the same thing over here. This is why this pencil looks broken, right? So I have this pencil in a beaker full of water, and it looks like it's over here in the water, but you can tell it's clearly not. That's because those light waves are hitting your eyes at different angles. Okay, and obviously in this first picture, this guy with the physics is fun in a pool It's the same situation. Okay. Now, those are the three ways that waves interact kind of on their own, but they can interact with each other too. So when waves are in the same location, they can overlap. It's called interference. So constructive interference will increase the amplitude. Again, that makes sense. Construction, think about building things up. Constructive interference increases amplitude. Destructive decreases the amplitude. So if two things, and this should have another, okay, here we go. So this is destructive interference. They're coming towards each other and basically canceling out. This is constructive interference. Two waves are coming towards each other and making a bigger wave. This is the principle that a lot of rooms, especially acoustic rooms, are built on. Things like concert halls and stuff like that. They want to minimize the number of destructive interferences that the sound waves have, right? It's a lot of times why they might have like big foam things up on the wall to catch the synthesis so they don't bounce back and interfere with that, okay, if that makes sense. So you want to minimize the amount of destructive interference when you want to hear that noise, okay? Now, standing waves, this is the only time we're ever going to talk about this basically. A standing wave is basically, if you think of a slinky tied to something or a rope tied to something and you holding the other end and you start going like this and the wave just kind of starts going like this, right? You don't actually get like that wave carry, if that makes sense. The wave's just kind of going like this. That's what standing waves are. And we're not really going to talk about that, honestly, very much at all. Okay. So the big things here: reflection, diffraction, refraction, constructive and destructive interference. And another thing that I kind of want to mention, the first two lessons. So again, I hope we're all pretty good on those. The one things I'll just tell you that I want you to remember with those are, know those the frequency and period and wavelength and wave speed and all that. Know those problems. Know the types of waves. So mechanical waves, electromagnetic waves, transverse, longitudinal. Know the different parts. Know wavelength. Know crest, trough, compression, rarefaction. Know amplitude, and know the definition of all those, obviously. And that's pretty much it. The one thing that I feel like I didn't mention is the particle motion compared to wave motion. So in longitudinal waves, you know how they're going like this? Think wave motion is the same direction as particle motion. In a transverse wave, the wave is going out, but what are the particles doing? They're going up and down, right? So in a transverse wave, wave motion is perpendicular to particle motion. That question will come up a couple times on quizzes and reviews and tests and stuff like that. So that being said, I hope this wasn't too quick and I hope I answered everything, but that's pretty much the chapter. So lessons 1 and 2, I know might feel kind of sketchy just because we didn't cover them this week that much at all. But hopefully lesson 3 is a fairly simple one that we can wrap our heads around. And again, as always, let me know if you have questions. Leave a private comment, email me, do what you need to do to get a hold of me. We can set something up. So let me know if you have any questions. Have a fantastic day.